In our first two sections of this chapter, we covered the three major factors that determine the climate on Earth: insolation, albedo, and greenhouse gases. In this section, we're going to go into a bit more detail on how different forces and events can and have changed Earth's climate over the course of its geological history. And we are also going to talk about the current climate period that we are living in and which forces have been the predominant ones in shaping climate in Earth's recent history. So the first one that we'll talk about is greenhouse gases. As you know now, greenhouse gases absorb heat and prevent it from escaping into space. They can be both naturally occurring and man made. So the big naturally occurring greenhouse gases are carbon dioxide, methane, ozone, and water vapor. Humans also emit other greenhouse gases like nitrous oxides and CFCs, as well as contribute to the output of carbon dioxide and methane. And one very important point that we want to take away about greenhouse gases is that tiny amount of them can cause large effects. You may remember from our previous chapter that 78% of our atmosphere is nitrogen, 21% is oxygen, and neither of those are greenhouse gases. So 99% of our atmosphere is oxygen and nitrogen. And then of that remaining 1%, greenhouse gases only account for a fraction of it. Carbon dioxide is the biggest one, coming in at 0.04%. So the bottom line here is that greenhouse gases make up a small fraction of the atmosphere, but they still have a big impact on keeping the earth warm. So, what may seem like very small changes in the concentration of those greenhouse gases actually amounts to significant consequences for the heat absorbing capacity of the atmosphere. And one more note here is that water vapor is something that can be removed after a few days in the atmosphere. Usually, that's its period of time that it lasts. Um, Methane takes 10 years before it is destroyed in the atmosphere. So, for any methane that's created either naturally or man-made, you can expect it to remain in the atmosphere about 10 years, and CFCs remain in the atmosphere for about 100 years. Another force that has impacted the Earth's climate by changing albedo levels is the activity of volcanoes and asteroids. Volcanoes have been both a heating and a cooling effect on the climate, depending on whether you are looking in the short term or the long term. Eruptions release carbon dioxide into the atmosphere, which is, of course, a greenhouse gas. And so, in the long term, this enhances the greenhouse effect and warms the climate. However, in the short term, and by short term, we are still talking on the order of months or years, these same eruptions release ash and sulfur, which causes the climate to cool because it increases the albedo of the atmosphere. The ash and the sulfur block sunlight from reaching the Earth's surface and instead cause it to reflect. Large asteroid impacts have a similar effect because of the large amount of ash that they kick up into the atmosphere. Because of this, both volcanic activity and asteroid impacts have historically caused mass extinctions, which are periods of time where at least 75% of species go extinct. They pollute the atmosphere with so much ash that the lack of sunlight can mean that plants don't have enough light for photosynthesis. And because plants are producers that support the rest of the food chain, it can cause the whole food chain and consumers that depend on them to collapse. Another factor that affects the Earth's climate is clouds. Like volcanoes, clouds can both warm and cool. They increase the albedo of the atmosphere and reflect light, which causes cooling. They are also composed of water vapor, which is a greenhouse gas that can trap heat and act as a heat blanket for the Earth. Which effect you get from the cloud cover depends on the type of clouds, its height from the atmosphere, and what time of day it is. For example, during the day when the sun is out, clouds typically provide albedo and therefore cooling, but during the night they're no longer reflecting solar energy and are predominantly warming the environment. As our climate continues to change and temperatures go up, climate scientists predict that there will be fewer clouds, which could make temperatures more extreme, both more hot during the day because you don't have the clouds to moderate the solar radiation with albedo, and cooler at night because you don't have clouds to insulate and keep things warm. And then two other forces that have changed Earth's climate are first, biological organisms. We've talked about how living things perform metabolic processes that either consume or release carbon dioxide and oxygen. And this does have an impact on the extended atmosphere. For example, you may remember us talking about the Great Oxygenation event in previous chapters, where cyanobacteria, who were the first photosynthesizers to evolve on Earth, were responsible for generating the oxygen that we have in our atmosphere today, as well as consuming significant amounts of carbon dioxide in the process. And then finally, characteristics of Earth's orbit, tilt, and spin have strongly influenced patterns seen in Earth's climate throughout its history. At any given period in Earth's history, each of these various forces have played a different role of the predominating force in dictating what the Earth's climate looks like. So, what about today? So, what about our current geologic period? What has been determining climate during our current period? Well, the current period that we are in is called the Quaternary. This period is defined as spanning about 2.6 million years ago up until present day. Remember, humans have been around for a little less than 200,000 years. So the start of the Quaternary predates us by a long shot. Climate during the Quaternary has not been static. It's characterized by alternating glacial and interglacial periods. During glacial periods, ice sheets have covered much of the northern hemisphere, while during interglacial periods, those ice sheets recede and the climate is warmer. Right now, and for about the past 12,000 years, we have been in an interglacial period called the Holocene. Okay, so what has caused the Earth to oscillate back and forth between glacial and interglacial periods throughout the Quaternary? There are three big forces that have caused this ebb and flow. One of them is orbital changes, which are gradual variations in the shape and size of Earth's orbit around the Sun. Also, tilt variations, which are gradual adjustments in the angle of the Earth's axis. You may remember from the last section that we're at about 23 degrees right now, but we haven't always been, and we won't always be. The tilt changes over time. And then finally, greenhouse gas dynamics. So, changes in the concentration of heat absorbing gases over time has also facilitated glacial and interglacial periods. Scientists estimate that there have been about 30 glacial interglacial cycles in the past 2 million years. And we're going to look at how each of these variables brings about the alternating glacial and interglacial periods. But before we do, let's talk about how we know this. What is our evidence? Because after all, the Quaternary has been going on for 2.6 million years, and humans have only been around for a couple hundred thousand. So, how do we know this? We know this by relying on sources of information called proxy data. Proxy data is information gathered based on preserved characteristics of the environment that can serve as a substitute for taking direct measurements. Obviously, we cannot directly measure what the temperature was on Earth millions of years ago, but we have geological relics of those times available to us that can tell us that information. One important source of proxy data is ice sheets in polar regions. These are huge areas of permanent ice that have existed for extended periods of Earth's history. The regions they exist in are so cold that they don't melt and are preserved over time. These ice sheets are formed from seasonal snowfall that gets compressed into ice over time, and then more snow falls on top of that layer, and more snow on top of that layer, and so on, such that the deep layers of the ice sheet correspond to the oldest ages. To give you some perspective on how far this record goes back, the bottom of the Antarctic ice sheet is about 800,000 years old. From these ice sheets, ice cores can be extracted. Ice cores are long cylinders of ice that are obtained by drilling down, sometimes several miles down, and those cylinders of ice contain many layers reflecting various depths and periods of time from the past. Knowing that the deeper you go, the older the ice is, we can estimate the age of a particular layer of ice because the ice cores can be stratified into visible layers, kind of like tree rings that represent each consecutive season of snowfall and freezing. And then looking closely at the layers, scientists can infer what the climate conditions were like on Earth at the time that the layer was formed. They do this by looking at variables such as temperature of the ice, the properties of the water molecules that the ice is made of, dust particles that are trapped in the ice, and gas bubbles that are trapped in the ice. So let's talk more about the type of information these variables provide. We'll start with what we can learn from the properties of the water molecules that make up these ice core layers. The chief property of water molecules that provides information about climate is their mass. Not all water molecules weigh the same amount. There is a natural variation in the weight across water molecules because these molecules contain different isotopes of oxygen. You may remember from chapter 2 that isotopes are variations of an element that have the same number of protons but have different numbers of neutrons. So, in the case of oxygen, which is one component of water, H2O, there are two oxygen isotopes that bring about different weights in water molecules. Oxygen 16 is an oxygen atom containing 8 protons and 8 neutrons, and you add them together and you get 16. And then oxygen 18 is an oxygen atom containing 8 protons and 10 neutrons. So oxygen 18 is a bit heavier than oxygen 16. And this difference in weight affects the way that the water molecules containing these different isotopes behave in the atmosphere. In the case of oxygen 16, which is lighter weight, water molecules that have this isotope of oxygen more easily remain suspended in the atmosphere as water vapor because they aren't as heavy. By comparison, water molecules containing the oxygen 18 isotope are more likely to condense out of the atmosphere as precipitation because they are heavier. So, in the grand scheme of global precipitation patterns, the oxygen 18 water tends to condense out as rainfall over middle latitudes of the planet, while the oxygen 16 water remains aloft and can make the journey through the atmosphere to the polar regions where it falls out as snow and turns into ice. However, some of the heavier oxygen 18 water does make it to the polar regions, and the specific amount of oxygen 18 water that makes it depends on how warm the Earth's climate is at the time. During warm climate periods, there is more heat energy in the atmosphere, and this helps keep the heavier oxygen 18 water to remain suspended. During cold climate periods without the extra heat energy, the oxygen 18 is more likely to drop out as rain in the mid latitudes. This means that when you're looking at a specific layer in a polar ice core that corresponds to a specific time period, and you see a higher proportion of oxygen 18, this means the climate must have been warming during the period when that layer of ice formed. When you see less oxygen 18 in the water, then the climate must have been cooler. This figure here shows you historical temperatures that have been extrapolated based on the oxygen isotope analysis method, going back 450,000 years. The black dotted line is our current temperature today for a point of reference. The blue and green lines represent the temperature data extrapolated from two different sets of ice cores in Antarctica that were drilled out of sites located about 350 miles apart. The EPICA site and the Volstock site, which you can see marked in red on the map at the right. And as you can see on the graph, these two independent samples of ice core data agree with each other very closely, and they show repeated fluctuations in the Earth's temperature over time. And this graph doesn't display it, but you can even look at ice cores that are even farther apart, such as the ones from the northern hemisphere, and they agree with what is seen in the southern hemisphere. There's also the red line, which is the volume of ice. And for this one, if you look at the labels on the vertical y-axis, low ice volume is actually represented on the top, and high volume of ice is on the bottom. So you can see how, as the global temperature goes up, as seen in the oxygen isotope data, the amount of ice is lower because it's warmer and not as much ice forms during that period. And so the volume of ice undulates in rhythm with the temperature of the planet. Two other pieces of information that we get from ice cores, other than the oxygen isotope data, are dust particles and gas bubbles. Dust from geologic events like volcanic eruptions gets incorporated into the layers of ice, and this can offer a richer picture of other factors that may have contributed to changes in the climate at the point in time. In the ice core pictures you can see on the screen, you can see a very clear volcanic ash layer in the middle of the cores. In addition, scientists can use the amount of dust in a layer of ice to determine how dry versus humid the air was on Earth at the time, based on the principle that dry air carries more dust than moist air. Also, as the snow is getting compacted into ice, tiny air bubbles get trapped in the layer and effectively preserve a little sample of the atmosphere from that period in the Earth's history. We can actually look at the gases contained within the bubbles and figure out what the proportions were of different gases in the atmosphere at the time. And these analysis shows that periods with a higher concentration of carbon dioxide correlate with higher global temperatures as extrapolated from the isotope data. This figure here shows on top in blue temperature changes over the past 50,000 years of Earth's history, determined from oxygen isotope analysis. And then in green below, it is the concentration of carbon dioxide observed in the trapped gas bubbles and the corresponding ice layers. And again, as you can see, this is very strong correlation showing higher carbon dioxide concentrations being associated with higher temperatures. The red line on the bottom is dust particle concentration, which remember is an indication of how dry versus humid the air was at the time. One final related piece of evidence to talk about while we're on the topic of ice cores is ocean sediment cores. Ocean sediment cores are long cylinders of sediment material that gets drilled out of the ocean floor. And like ice cores, they contain various layers spanning different time periods. With ocean sediment cores, however, they cover an even longer time period than ice cores. Instead of looking at a timescale of hundreds of thousands of years, ocean sediment gets deposited over the course of millions of years. So the geologic and climate record that we get from ocean sediment cores spans the entire Quaternary period and beyond. And when we do an isotope analysis on those ocean sediment cores, we again see an oscillation between warm and cold periods. We also see that over the past 3 million years or so, the Earth's climate has been on an overall cooling trend on average, but there are still very dramatic swings between warm periods and cold periods. And right now we are in a warm period. Oops. So this gives you a picture of some of the ways that we know about what climate has looked like over Earth's history. And we know that the Quaternary has been marked by these alternating glacial and interglacial periods. In our next section, we'll look at the specific ways that changes in the characteristics of the Earth's orbit have facilitated this alteration between glacial and interglacial periods. And that is the end of this soft chalk uh, page.